probably fourth or fifth time now. And my talk today, and as shown in the previous page, and was done by Dr. Dae-Pong Kong, and as part of the Marie Curie project funded by the European Commission. And the work was also supported by Gongquan Wang, who's here in the audience, as well as Ping Ping, who was a former Marie Curie fellow in my group. And I will also take this opportunity to make a small advertisement. And if any young researchers in the audience with good journal papers interested in being a Marie Curie research fellow, please do email me, and my email address is over there. I'm always looking for good researchers, and they are the secret to success. So, and I'm going to talk about this from single cell development and thermal runaway propagation in clusters. And that should lead to modules and packs, but we are not there yet, at least my group. And then I will give some examples, and I will make a concluding remark, but I will leave that on the screen for you to read because I want to see something else in that. So Michael's talk, and just minutes ago, is a very good introduction to what I want to say. You may remember Michael showed this swollen and of cells and battery packs. And he also showed that during overcharge and discharge, or charge and discharge, there might be the increase of strain rate, which leads to cell expansion, and eventually it tip over and went into thermal runaway. So my talk is about thermal runaway from slight overcharge and discharge. And this can happen during malfunction of the charging system and some imperfection during the manufacturing process of batteries, and as well as unbalanced charging current between the different cells in the system, in the pack. And again, inconsistent in battery aging. And we all age differently, every one of us. The same battery cells, they age differently. Some stay young forever, some age quickly. And if they are together in a pack and being charged, discharged, and used together, and some problems might occur. So what's our motivation? And I'm a strong believer of experiments, and the industries need to see what's happening when batteries malfunction, and to accept that. They won't believe it from what our models predict. However, during the development of batteries, and it takes many, many efforts and trial and error. And if they all do it experimentally, it's not only costly, but also for overcharge and discharge, it is a special issue. Because under thermal runaway caused by slight overcharge and discharging, they have a long incorporation time. It may take days for that to develop. And if you want to reproduce that in experiments in the lab, it's costly and time consuming. So we say that developing models, validate models, and using the models to assist the optimization and during design process could be a cost-effective way and for manufacturers as well as researchers. And so we went into 3 steps, from single cell to clusters. And from clusters, we should move to modules and pack levels. But we haven't got into that stage because the funding finished, and also the application eventually. And so I will talk about the development of thermal runaway and in a single cell. I must say that all the things which I present today, they are published materials. So they are in the open. I think the paper came out last year and last 2 years. And so single cell thermal runaway. So what we looked at, some of you may know that in my group for years, since year 2006, we have been developing models and within the frame of open source safety code open form. And we developed models for thermal runaway caused by overheating and by mechanical abuse like layer puncturing and previously. So what we have now moved here today is we build on the thermal runaway model we previously developed, but we look at the voltage evolution. Sorry, the E was missing from there. And then we added modules for temperature evolution and when the voltage changes during charge and discharge. And that complex diagram, I wouldn't talk about it. And so these are the formulas and which we consider step by step, and including the melting of the separator and the decomposition of the electrolyte and the reaction between cathode. And talking about electrolyte, and I won't say we are bad, we are actually now doing experiments through a current Mercuri research. We are looking at ignition of the vapor from electrolyte and by hot particles. And we are currently working on that, but the papers are not out, so I cannot talk about that. And so importantly, for charging discharge, we look at the voltage evolution, and accompanied by that is a heating caused by that, and as well as the boundary conditions. And obviously, we consider the heating that is generated, but the dissipation of that heat is incorporated in the CFD model already. So these are the experiments done at Chennai University of Petroleum and Dr. Kong's home institution, and they look at the NCM, LFP, and ALCO cells, and they did experiment internally to assist the model validation. And there are different cutoff voltages for these cells which they used. And so this is the capacitive feed which we are looking at for normal cycles. So it's a normal cycling and charge and discharge. And for different cells is listed there. And so on the top, we're comparing the voltages between predictions and the measurements. At the bottom, it's the temperatures between predictions and the measurement. And we are getting reasonably good agreement. And another important thing, if you compare the left, which is LFP, middle LCO, and on the right-hand side is NCM, what we can see is that LFP, which is believed to be a safer battery comparing with NCM, the capacitive feed is not obvious. It's not obvious over the cycles. And while the NCM does feed and more, if you look at the top, the last curve didn't go up as high at all. And so on that basis, we continue the validation of the voltage and as well as the temperature and during thermal runaway. So this is during thermal runaway now. And so these are the curve, the predictions, the quantitative comparison. I want to go back so I can talk about that animation again. If I go back to one page, come again. So you can see that the thermal runaway started from the bottom and to the top. And the reason for that is it's not because it's always going to be like that. So in the experiment, the cell was set on the ground or whatever they did the experiment, and the top is open. But in reality, the cells are going to be fixed into plastic frames. So the thermal runaway during slight overcharge or discharge may not necessarily start from the bottom, like what's shown here in our experiments and predictions. Because we put it on the ground in experiments, so there's limited heat dissipation from the bottom. And the different situations will be different. And now we are looking at the voltage. the overcharge voltage and the propensity to thermal runaway and the evolution. So what we can see here is that, and the overcharge, and if we increase the voltage, it would shorten the time to thermal runaway. So the cells would enter into the thermal runaway more quickly, but they don't have much effect on the peak temperature on the left there, and whichever battery it is. And what has more effect on the peak temperature during thermal runaway is the state of charge. So is the battery fully charged or it's only 50% charged? And that affects the peak temperature quite a lot. That's why during transportation, for example, or during storage, like the fire in the Korea factory last year, and they put pulse batteries there, they were all fully charged, 100% SOC. And in terms of the current, again, and what we found is that increasing the series would increase the rate, the temperature rise, and then also shorten the time to thermal runaway. And it's also interesting that the LFP cells are most resistant to TR, while the NCM cells are most prone to TR. I almost want to say something else about the LFP cells in our current experiments, but I'll refrain from that. As I said, it's not published. And now this is important because I put in red the safety implication there. The reason I want to say is that we do find that if we introduce convective cooling, this is simply by air. We just, in the simulation, we just put some velocity there. We impose it as a boundary condition, and there was a convective flow trying to cool the cells. And what we found is that by increasing the convective cooling, it would lengthen the evolution time required to thermal runaway. And if the velocity is increased above 1.0 meter per second, for example, even with an environmental temperature of 70 degrees centigrade, and it could prevent the cell from going into thermal runaway. So I think this has safety implications because although it's not always economical to introduce convective cooling, but in certain situations, I'm trying to think loudly myself. I mean, in cars, we have air conditioning in the summer. Why can't we direct that part of that air conditioning to cool our battery packs? Because the system is there. That's my thinking. I'm an academic. It's down to manufacturers to explore whether that's practical or not. Okay, now moving to propagation of thermal runaway from one cell and in a module to another, and from module to packs. And so we need to add additional models and submodels. What we call is to consider the electric head, the ohmic head, and the polarization, reversible head of Bill's reactions, and all these things. And so we added all those on the top. And, but we neglected the heat loss due to ejection of those gases and particles during thermal runaway, and even before when the venting just started. And we simplified the model. One important thing I think modeling batteries is we need to make simplifications, otherwise you will get lost. Too many details may not necessarily help. And I'm always of the opinion that we should also use quality experimental measurements and to replace some of the detailed and electrochemical reactions some of us put in our models, because chemistry of battery materials move very fast, materials change rapidly, and developing detailed models and may not pay off in time. And sometimes it's more efficient to use simplified models and use ARC test, for example, which my group typically use ARC test results to bypass some of the detailed reactions. And so we use these layers to connect the cells and to mimic the heat conduction and heat transfer between them. And we did some validation, because the validation we have for prismatic cells in a cluster is NCM prismatic cells. So we did a validation initially with the prismatic cells, and this is a single cell. So we are comparing the predicted temperature with the measured temperature. And during slight overcharging cycling here, and so we are comparing that. This is a single cell, and then we move to looking at the cell in a cluster, and this is a 5x9 cluster as shown there, and the middle one, the 3 and 5, that's the cell which went into thermal runaway, which was triggered into thermal runaway initially. So we have 10 AH prismatic cells, and experiment by Sun et al. And between the cells, and they have aerogel as insulation material. And so what we are looking at is, in the simulations, we were charging and discharging continuously, because in the model we can set up that easily. And however, in the experiments, and once they got a cell into thermal runaway, they stopped the charge and discharge. So what you can say that on the right-hand side, and the dashed line are the experimental temperatures, the dashed lines of different experiments, and then on the the solid lines are the predictions. So we got a slightly different peak temperatures. And part of the reason is that because we are continuously charge and discharge, so we are losing the state of charge from 100% in this numerical simulation. But in the experiments, once they had the initial cell went into thermal runaway, they stopped the charge and discharging. So their cells almost returned the initial 100% SOC, and as a result, they have a high peak temperatures. So that's why we see that differences. It's the differences between the setup conditions. And so that's the animation. So what we can see is that the propagation speed is faster to the shorter end, and so it's this direction, vertical direction, if you look at the screen, but slower in the horizontal direction on my screen. This is because the shorter length and there's a short path for heat dissipation, and the heat gets out to the environment more quickly, while in the longer direction, this way, it's a long path for heat transfer, and so the heat loss would be slower comparing with the vertical direction. And now we are looking at the insulation materials. And we have 4 types of insulation materials with different thermal conductivity. And aerogel is the one with the lowest heat conductivity, so the highest insulation capacity. So what we can say is that, and it's not from this graph, it's from the next graph. It's easy for me to talk about it. So what we can say is the positive side, and there's also the negative side. The positive side is if there's insulation material has the higher insulation capacity, like the aerogel, and that's the one on the left. It can shorten the time. It can shorten the time for propagation of thermal runaway. So that's the time for propagation of thermal runaway. And it can also reduce and the peak temperature and during thermal runaway propagation. However, with a higher insulation capacity, it also impedes heat dissipation from the cells. And because of that, potentially, it could make the initial cell going into thermal runaway more quickly, So that's what we see here. So the first cell went into thermal runaway 6330 second. And while the other insulating material, like the last one, I forgot what's the name of that, took 8,000. So they are positive side as well as the negative side. And in terms of chosen insulation materials, that's why another reason I believe some models can help manufacturers to optimize that choice. And this is looking at the thickness of the insulation. And we are changing from 1 millimeter to 20 millimeter. And again, it's easy to look at this one. It's a similar story. And the thicker the insulation material, and the better capacity it has to prevent propagation or slow down the propagation, but it restricts heat dissipation. And so the first cells and the time to the thermal runaway of the first cell, and it's much shorter, and 60-30. So there was a balance, there was a compromise, and one has to try to achieve. And so the ambient temperature, naturally we can see that the higher temperature, the propagation can happen more easily. I don't need to talk about this in detail, conscious of the time. And this, again, it's a similar thing. So lower the ambient temperature, it can actually not only slow down the process for the initial cell to be triggered into thermal runaway, but also slow down the propagation. That goes back to my comment a few minutes ago. And why can't we use the air conditioning system, which is in place in most hot places, to help cooling the battery packs as well? And it would take some system design, but that can assist battery management on its own. In my mind, battery management needs to be considered in the context of the environment, not just on its own. So some quick results, and this is for cylindrical 21700 cells and without validation. Just illustration, so we consider such things, and cylindrical cells, 6 of them, and we try to model the thermal runaway propagation, and in this case, it did not propagate. And the reason for, part of the reason for that, and in the simulation, we set the same condition of slight overcharge and discharge to all the cells. So they were uniform, and they didn't propagate. And then in this one, we tried to do differently. We had more cells in the cluster, and so we have 4x4 16 cells. And what we did is we overcharged cell 22 to thermal runaway, and other cells were going through a normal cycle. So they have different conditions, imbalance in the system and in the cluster. And what we can see is that these are the temperature evolutions. And so we can see as time goes, and from about 1900, we started getting some cells, temperature goes up, and again, and it varies monitoring points and in that box of clusters. And so this is starting from cell 22. We can see it's propagating and to the surrounding cells. And what's interesting to notice from here is that although from slight overcharging and discharge, the time to the first cell going into thermal runaway takes longer than overheating and layer puncturing. But once the first cell started the thermal runaway, the propagation between cells and does not take that long like the initial evolution. And so this is just another case, and with the cell on the boundary, on the side, on the edge, cell number 12 went into thermal runaway, and then we were tracking the temperature of different cells and the monitoring points there. And And so this is another looking at images, and we can see the propagation. And again, it took about the same time for the first cell to go into thermal runaway, and then it's the nearby cells and which were triggered into thermal runaway and propagates eventually between all the cells and in the cluster. So we look again at the effect of convective cooling, and in a situation like this and in a clusters, and we considered this time, rather than adjusting velocity like the previous simulation for the prismatic cell clusters, we are adjusting in the numerical model the convective heat flux. So this one is with 30 watt per meter square K, and on all the surfaces of the cells. And so we can see that, and the propagation slowed down. It does slow down the propagation, and with the convective cooling, and but it did not stop it in this case, and it has some effect. And then if we increase the heat flux to 70 watt per meter square K, and what we can see is that, and we still stay at a charge rate of current rate of 3C and the voltage of 4.2 watts. And what we can see that even after 2 cycles and of overcharge and discharge, and at 4.2 watts, and with a cooling coefficient of 70 watt per meter K, and under environmental temperature, I did not put environmental temperature there. I forgot what it is, unless Gongqian can tell me. So anyway, the cells didn't go into thermal runaway with strong convective cooling. And so the convective cooling does have some effect. So to conclude, and I will let you read this while I want to say something else, which I said I wanted to say, because I'm trying to do some looking at the literatures. And what I found is that there's a lot of research going on about battery safety, materials, heating, propagation, all kinds of research, but mostly are looking at the batteries and in automotives, electric vehicles, or in energy storage. There is another important area which is important to China. Although I mean Hong Kong is part of China, so I want to see this. China, we are still going to dig out cores. We are still going to extract cores and use cores in an efficient and cleaner way, and there are methods being developed to use coal more environmental friendly. And also there are ambitions of the Chinese government, and it's not just ambition, it's a plan, and to get the coal trucks, the man trucks, and to be fully electricalized, and also for robots to replace the miners to work under the ground. And in those environments, the batteries are exposed to environment with more moisture and underneath the ground, and also there are more dust. So the moisture and the dust would affect the evolution of batteries during their normal operation. And also, if there are more robots going to underneath the mines and to work there, they need to be charged and discharged underneath the ground. So there should be some more researchers and to look at those issues and to take on the challenges. And I was looking for papers about those for mine environment. I didn't find any. Maybe I missed some, if some of you know. So with that, I think I will stop my talk. Thank you for listening.
Thank you, Professor Wen. Now we have about 10 minutes of Q&A time. Please just raise your hand and let our volunteers know. So I'll ask the first questions. So Professor Wen, you are expert in modeling. May I ask, what do you think is the most challenging part in simulating battery fire, and what's the difference between compared to regular building fire modeling?
I think it's the complexity, and as I mentioned during my presentation, with the battery fires, and there are more complexities, and with the materials, and there's more stochasticity in terms of the materials, and how the materials dissociate and react with each other, and also the materials, the evolution is much faster than building materials. And look at how many different kind of electrodes and the electrolytes and the cathode, and how they have been invented, and then how many research has been done to add different ingredients into those things to make them safer. So that's why I keep on saying in battery modeling, whether it's files or it's the evolution of thermal runaway, is one have to make decisions to simplify. Otherwise, it's difficult to get anywhere. To simplify as much as you can. And another important thing is, with the thermal runaway in practical situations, in models and in impacts, there's another complication. Whether the battery fire burn a hole a lot in the casing, and whether there's a hole in the casing or not, that makes a huge difference to thermal runaway and to its propagation. So that needs to be considered, because I know people have done tests with the cluster batteries and they put them in the open without any casing. Yeah, they burn, and the first cell go into thermal runaway, but the fire went up. It didn't cause propagation. So the casing caused a lot of problem. And then how that casing is arranged, how many millimeters gaps between the cell top and to the casing, that can be critical. And for example, one calculation we did for Jaguar Land Rover in a UK project, that I don't think it's in the paper anyway, but I can talk about it. It's the casing, the gap between the top increasing from 5 millimeter to 8 millimeter makes a big difference between without considering this insulation and the different materials, different gap between the cells. Gap between the cells, no, there's not much flexibility in that. For a car, EV battery, you have limited space. But even the gap between the top and the casing, 5 millimeter and 8 millimeter, can make a big difference to the propagation. But sometimes in cars, you can just not afford that 3 millimeters. And the space is so precious. And so there's a lot of challenge, but many of the models we have done, we are not considering all these details. We are looking at the science, but there's a lot of practical issues which the models can eventually hope one day can be used, and by the manufacturers to look at these issues. But obviously, as Michael hinted in the beginning, and we academics, for us to look at those issues, we need to be funded by industry, because for academic research, we needed to push forward the science. So there's a big step between science and to technology and to engineering practice. That's a real challenge.
Thanks. Yes.
Hello, Jennifer. Thanks a lot for your introduction for the so-called thermal runaway propagation. During your test, is there any real LFP battery packs you used, and what is the scale and what is the size? Because according to the different power capacity, the thermal runaway propagation shall be different. And what's your conclusion and what's your experience about it? That's my question.
And if you change so we, in this calculation simulation for this work, we only did that particular one. It was in the slide, it would be online, so how much capacity was that? And but if you change that, it would be different. And we also, now I remember the LFP thing, which I said, we actually published the paper in power sources. And we did observe in experiments LFP cells and went into thermal runaway in the laboratory and caught fire. So they are not fire resistant. They are safer. It takes longer time, but it can still go into thermal runaway fire.
Yes, exactly, because according to the rising of the capacity of the LFP cells, right, or packs.
But in this set of parameters, they were safer. Okay. So all the conclusions here are limited comparatively. You can look at these conclusions comparatively, they are safer. And also in terms of quantitative thing, and the quantified results came from quantified inputs. So the quantified results are based on the quantified inputs we put into these models.
Thanks a lot, Jennifer.
Yes.
Dr. Jennifer, and I'm a student from University of Science and Technology of China. My question is, when we verifying the battery temperature with a model and experiments, we only use just one temperature compression to determine it. So if it's reasonable. And we all know that the temperature of the larger single cells, the temperature distribution of it is relatively wide.
Yeah, you are absolutely right. You are absolutely right. In experiments, it's difficult to measure temperature and 3D and for a cell, for a cluster. And in my project, joint industry project with Jagannath Zower and my ex-colleague from WMG, and WMG did insert thermocouples into the cells, and we sent to THT to do some measurements because our partners could not test the cells which had been modified. And so we found there was a minimum 100 degrees centigrade difference between temperature inside the cell and on the surface. And also there's a temperature variation in our predictions. We have models which can predict the three-dimensional temperature evolution. Rather than treating the cell as a lumped capacity, lumped body, we have conducted three-dimensional models which show the temperature differences of the cells. So they are great. There can be a lot, but we are limited by financial resource. It's not practical to ask experiments and to measure three-dimensional temperatures and to put sensors everywhere. Also, these thermocouples, they can be intrusive to the evolution.
Oh, thank you.
Conscious of time, thank you. Yeah.
Okay, so let me finally invite Professor Jinhua Sun from University of Science and Technology of China to give our plenary speaker the certificate.